In this tutorial, I will show you how to virtually plan an orthognathic surgery case using Mimics Enlight CMF. Starting from the CT images and dental casts, we will go over all the steps needed to plan the case and in the end design a dental splint. To import the images that we're going to work with, click on From Images and then find the directory of the folder where the DICOM images are located. Once selected, the software will show a preview of the image series. Click on Open to continue with the selected images. The first step in 3D planning is making the 3D models that we are going to work with. And there are two options to do this. We can either manually segment the skull and soft tissue using the built-in segmentation tools, or we can use the AI-enabled automatic segmentation option by uploading the file to the Mimics Flow platform. Here we'll first show the steps for manual segmentation. Click on Orthognathic and Trauma Planner and continue at the bottom of the page to start planning. At the top, we can see the workflow navigation bar, and these are all the steps that we will take in the process. Although some steps in the workflow are optional, most steps will need to be finished before continuing to the next one. Here on the right, you can find the general toolbar regarding the view settings, measurements, as well as import and export options. The view will automatically change depending on the actions we will take during planning. And on the left-hand side, the actions are explained in the workflow page. In the preparation step, we can check the DICOM information by right-clicking on the image series and selecting Image Information. Next, we are going to segment the skull and the soft tissue because both are needed later on. Let's start with the skull. After clicking on Skull, we can see that the threshold already has been set to match that of bone tissue. We can still change the maximum and minimum if needed, but for this case, we can keep them as they are. To change the contrast of the image data, you can hold the right mouse button and move the cursor up and down or left and right, and this will change the visual contrast window. Click Apply to continue. Sometimes it is possible that unwanted voxels are included when segmenting the skull, and in this step we will get rid of them. With the Erase tool, we can draw around those voxels and remove them. This also works in 2D on the right-hand side. Once we are done editing, we can click on Finish and let the software calculate a 3D model based on our segmentation. Now we can do the exact same steps for the soft tissue. And here again, the threshold has been set automatically to include the soft tissue. As I mentioned earlier, there's also a second way to create 3D models. Instead of doing it manually, I'm going to show you how you can request the automatic segmentation via the Mimics Flow platform. Just as before, you need to start by loading in your images, and then you can log into the Mimics Flow platform and start requesting the segmentation. First, you need to create a new case, enter a title, and then add all the additional details you would like to include. And once the case is created, you can select the algorithm you would like to use and submit the request. The case will be uploaded to the cloud, and once completed, you can load in the final segmentation. And as you can see, the teeth and the root canals were also segmented automatically. Now that we have our skull and soft tissue model, we can continue to the next step. The quality of the teeth on CT scans is usually not good enough to do accurate planning, and it is even worse when there is scatter on the CT images. To solve this, we will now import a high-resolution model of the teeth on the maxilla and mandible respectively, and put those on our model of the skull. Click on Maxilla, and then find the STL file of the maxilla cast in your directory. Then do the same thing for the mandible. Now, once the two models are imported, we need to put them on the correct location on the skull. This is done automatically by the software. The only input that it requires from the user is an initial alignment. And this alignment is done by placing at least 3 points on the cast and the skull. After this initial alignment, a calculation will start running to make sure that the casts are aligned perfectly to the teeth in the CT image. Let me show you what that looks like. Here I will place a point on a molar on the skull and then on the same molar on the cast. Then I will do the same for a point somewhere anterior, and then again for a molar on the other side. And we can do the same thing for the mandibular cast. This is the only input that the alignment algorithm needs. After pressing finish, the algorithm will start running and align the cast to the teeth on the CT scan. And after some time, this is what the result looks like. If needed, the teeth can be repositioned manually again with the tools indicated next to the maxilla or mandible respectively. You can check the alignment by comparing the contours on the planar views by scrolling through the image stack. Here, in this case, it is not necessary since the alignment is perfect. The last thing we have to do in this step is to review the fusion of the casts with our skull. We can indicate where exactly the teeth need to be replaced. If you want to change the cut, click Edit and drag the red control points to make sure that the teeth are entirely included in the volume. Once this is the case, we can click on Next. Here in this step, we have the option to manually trace the inferior alveolar nerves. I say option because this step is in fact optional, but for this specific workflow, I'm going to do it to show you what it looks like. To make the tracing easier, the images will be resliced so that the entirety of the nerve is located somewhat in the same plane. The panel here on the left-hand side tells us where to place the points in order to reslice the image. We only need to place one point on the mental foramen and one point on the mandibular foramen, and then the CT image is automatically resliced, as you can see here. Now we can start tracing the nerves by placing points on the CT image. While placing points, we can scroll through the images to make sure that the nerve canal is nicely visible. To stop tracing, either press Escape or double-click when placing the last point. And now we can do the same for the patient's left side. Once this is done, we can move on to the next step, which is setting the natural head position. Setting the natural head position starts by indicating the Frankfurt horizontal plane. This is done by indicating a point in each ear canal and a point on the inferior border of each orbit. Setting the Frankfurt plane is actually just the starting point for the next adjustments. After clicking on Finish, we are prompted to the next screen where we can adjust the position of the skull in the 3 orthogonal views. We can drag and rotate every orthogonal plane in order to set the natural head position. The pink line in this view indicates the mid-sagittal plane, where the blue lines provide visual aid. The grid in the viewport can help us with that as well. And once we are done, we can click on Next, and that will bring us automatically to the cephalometry step. Here we can place anatomical landmarks which will later be used in the measurements when planning the procedure. The panel on the left-hand side here tells us where to start placing the points. You can customize this list and select which points, measurements and planes you would like to use. The convenient part here is that every time a point is placed, the view changes so that placing the next point is much easier. We don't have to manually turn the model around. Once we're finished with placing all the points, we can review them one more time and adjust them if needed. Once all the points are in place, we can continue to the next step, which is performing osteotomies. Here we have an overview of the possible osteotomies you can perform in Enlight CMF. For this specific case, we are going to do a Lefort 1 cut and a bilateral sagittal split osteotomy, or BSSO for short. Now, before we do the osteotomies, I want to emphasize that the case we are about to plan is not necessarily clinically accurate. The goal of this tutorial video is just to show you how the tools work. For actual planning, you should always consult with a trained healthcare professional first. And with that being said, let's start with the Lefort 1 osteotomy. We just need 4 points as a user input in order to generate the osteotomy plane. And again, here in the panel on the left, the software tells us where to place those points. After placing the points, this is what the generated osteotomy plane looks like. We can move the red control points around to adjust the shape of the osteotomy plane or rotate the whole plane when using the coordinate system option. We can visualize the teeth by toggling them on in the panel on the left-hand side. And once we're ready, we can click on Split to perform the cut, and then on Finish to go back to the osteotomy selection panel. Now let's move on to the BSSO. Just like with the Lefort cut, the panel on the left shows hints on where to place the points in order to construct the osteotomy plane. And here we can also adjust the control points to change the shape of the plane. Toggle on the teeth and nerves to help with positioning the osteotomy plane. It is possible to rotate it when choosing the coordinate system icon next to the plane in the panel. Click on Split to confirm the cut, and then click on Ramus L. And there perform the exact same steps. Once all osteotomies are done, we can move on to the next step. This is where we set the desired occlusion for the patient. In Enlight CMF, there are two ways to do so, either with a 3D model of the occlusion or by setting the occlusion virtually. For this case, we are going to do it with a 3D model. And the model is a combination of the maxilla and mandible set to the desired occlusion. Click on Occlusion Cast to start the workflow, and then import the STL file of the cast. The next step is to register the mandible and maxilla of the composite model to the mandible and maxilla of the occlusion cast. And this is also done by placing 3 corresponding points on both models. Once all the models have been placed, the software will use the points as input to run the registration algorithm. And this is what the end result looks like. This flaky pattern is normal and actually tells us that the models are in the exact same location. You can check your alignment and make some changes if needed. Then click Next to move on to the reposition step. In the osteotomy step, we have created different parts of the skull, and now we can reposition them according to our planned outcome. To move a certain component, select Move in the left panel, and then select the part that you want to move. You can move multiple objects at the same time by holding Control when selecting them. An interactive coordinate system will appear which can be used to move our parts around. We can either click on each direction for incremental movements, or we can click and drag for bigger movements. By pressing the shortcut Shift and G, you can change the interactive coordinate system between translation, rotation, or both at the same time. To select the whole occlusion, you can toggle it on the left-hand side. While moving parts around, we can keep an eye on our measurements in the panel on the right-hand side there. It is possible to create reference objects for different alignments or for special cases. Simply right-click the part you would like to use and choose Duplicate as Reference Object. You can also import any STL at this point in the process. This could be, for instance, a separate part from an Neurio scan that you would like to include in this planning. The Align tool can then be used to overlay the imported part with your planned positions or reference objects. Here we can also use the soft tissue that we segmented in one of the first steps. After having repositioned the different parts of the skull, the software can make a simulation of how the soft tissue will have changed. Click on Simulate Soft Tissue to create the simulation. In the object list on the bottom left of the viewer, you can toggle on both the soft tissue based on the CT and the planned one. And once we have our planned outcome, we can use this information in the splint design step. This is the final step of the entire workflow. Here we can design the splints that will be used during the surgery. We have the option to design an intermediate splint and the final splint that fixes the desired occlusion. In this workflow, we will just focus on the final splint, but the steps to design an intermediate one are almost identical. After selecting the final splint, we can start by indicating a rough outline of where the splint should go. The workflow panel on the left here tells us where we have to place the points. These points are then used to make a general shape of the splint. After having placed some points, click on Apply to generate a shape. We can easily modify the shape of the splint by clicking on Edit Shape and dragging the edges around. The shape of the splint will be updated accordingly. Make sure to click Apply after you've done editing the shape. We also have the possibility to add wiring holes to the splint. Here we can specify the diameter of the wiring holes, and then we can simply click on the places where we want them to be. Once we are finished, we can click on Apply to actually place the holes. If we are happy with the final shape of the splint, we can go ahead and add a label to it. Here you can control its size, direction, and the text. If it's needed, we can add multiple labels too. After that, we click on Finish and then on Next. And now we've completed the planning of our case. In this final step, we can export everything that we have done in the previous steps. All the 3D models can be exported as STL files, the cephalometric analysis as a CSV file, and the natural head position can be exported as an XML file. You can also generate a report in PowerPoint format. And here we also have a nice comparison between our pre-op situation and the planned outcome. And with that, we've reached the end of this tutorial.